Good morning. First, we talked about the science of climate change and what's actually driving it. And yesterday, then, we talked about the Arctic and the Antarctic, the polar regions, and what is called polar amplification and why that is so important to climate change. Today, I'd like to discuss what's actually happening in the polar regions to the flora and fauna, and more particularly the food webs and the effect that that is happening. And as you know, there's thousands and thousands of very unique species, both plants and animals, that live in the Arctic and the Antarctic. And these are going to be radically affected by climate change, perhaps among the first creatures on the earth to be affected. But before we can talk about this, we've got to talk about the other CO2 problem. And that problem is ocean acidification. If you look at the Earth's carbon balance, and down in the bottom left-hand corner, you can see fossil. And it's 12,000 gigatons of fossil fuel. 12,000 billion tons are known fossil fuel reserves. As we burn these, we put about 6 gigatons a year. That's 6 billion tons a year into the atmosphere. Now, the atmosphere then redistributes that. And if you look at this chart, you can see that about 122 of that are coming down into the Earth. But the Earth then, through animals breathing, respiration, puts out carbon dioxide, and through animals and plants that are dead, decaying, puts out CO2. The net effect is the terrestrial environment takes up about 2 gigatons a year. The ocean also takes up about 2 a year. And so the atmosphere, 6 in, 2 out, 2 out, the atmosphere is taking 2. So it turns out that everything is taking in about 2 a year. There's a big difference though. In the ocean, if you look at the total fossil reserves, it's 12,000 gigatons. If you look over here in the ocean, in the surface waters, we have about 600 gigatons, but that's recycled every 6 years. We have in the middle environment about 7,000, takes 100 years. In the deep ocean, the benthic environment, the very bottom, we have about 30,000 gigatons. Takes 100,000 years to recycle. But in the very, very, very bottom, in the sediments at the bottom, we have not thousands, we have 30 million gigatons of carbon. And that carbon lasts down there for 100 million years. The ocean is a huge carbon sink, which takes CO2 out of our atmosphere. If it wasn't for that, climate change would be progressing much faster. But it's taking it out at a huge price to the ocean in ocean acidification. Now, let's go back, and I know this will bring back bad memories to many people, but we're going to discuss chemistry for a few minutes, and you think, oh my gosh, I remember that from high school. I just want to talk about pH. pH is a measurement of the concentration of an acid or base in the liquid that you're talking about. If you have a pH of 1, you're talking really strong hydrochloric acid, battery acid. Neutral is 7. That's what water has. And if you look down here at lye, for instance, and ammonia, you're finding 12 and 13. These are called bases. These are called acids. The average ocean water has a pH of about 8.2. It's slightly basic. When we absorb carbon dioxide in the water here, the H2O plus CO2 goes to carbonic acid. Carbonic acid is a very weak acid, but it disassociates easily and comes apart. So when it comes apart, it can come into hydrogen ions and carbonate ions. Carbonate ions are incredibly important to the ocean, as we'll see later, for carbonate buffering and for other things. And so this increases the free hydrogen ion concentration. As we said, this is a measure of hydrogen ion concentration, acidity. So that makes the oceans more acid. So the oceans are going up in acidity. If you look at oceans versus river water, it's very important to realize oceans are not just concentrated river water. The process of life in the ocean changes the ocean water very radically. If you look, for instance, at bicarbonate in the river waters, that mainly comes from dissolving limestones in creeks and rivers. When it gets into the ocean, it's 48.7% of the particulate matter here, is 0.4%. What happened to the bicarbonate? Calcium went from 12.4 to 1.2. Where did the calcium go? But you look down here and it goes the other way. chloride and sodium. Well, this is what makes it saltwater. The oceans, due to life in the oceans, are radically different than river water. And if you look at the very bottom of the food chain, the phytoplankton that absorbs sunlight, photosynthesis, they don't appear to be significantly affected by the pH. There's been a lot of experiments where we've put little phytoplankton in, 7.6, 7.7, et cetera. And the ocean is now down about 0.1. And they don't appear to be that affected. So that's a good sign. Let's look next then to understand what's going on in the ocean and why it's so important at what is called carbonate buffering. When the CO2 is absorbed, as we said, it goes into carbonic acid. And then that carbonic acid can go into two hydrogen ions and carbonate ions. And that can actually go back and forth. This little arrow means this reaction can go either way. And it's determined by the concentration on each side. I mean, for instance, if there's only this and none of this, it's going to go that way. It's going to go towards the right. And likewise, if there's too much of this, it'll come back. So it's an equilibrium, and they'll get to the equilibrium wherever it is. So one of the hydrogen ions can hook onto carbonate and form bicarbonate. That leaves an extra hydrogen ion floating around. That's so important because that hydrogen ion can come down and take a carbonate ion that's in the ocean, already there, and latch onto it and make bicarbonate. So the net effect of putting this into the ocean is it's taking carbonate out of the ocean and making bicarbonate, because when you put it in, you have two hydrogen ions. One of them can form bicarbonate here. You have an extra one. It can take a carbonate right out of the ocean. If you look at the studies on ocean acidification, a recent study in Nature pointed out that acidification is processing at a rate 10 times faster than it did in the Great Mass Extinction 55 million years ago. The concentration of hydrogen ions has increased 30% in the last 2 centuries. And equally as important, the concentration of carbonate ions, because of this carbonate buffering, has decreased by 16%. This is a graph here of carbon dioxide, here, atmospheric CO2, partial pressure of CO2, and pH. You can see the pH is drifting down. Now, as we lose carbonate, we're going to lose the ability to buffer acidity changes as we get more and more ions. And so the ocean will start to acidify at greater and greater rate because we're losing the ability to buffer the reaction by taking the hydrogen ions out of circulation. The hydrogen ions will stay and they will be acid. And the next thing is the most important, maybe not the most important, but one of the two most important, is it will continue to lose carbonate. We're going to lose carbonate out of the ocean. Now you ask, who cares? Well, seashells do, because carbonate is what they make seashells out of. If you're a seashell, you need carbonate to make calcium carbonate, which is seashells. And so you will find that shell-forming organisms of, I don't care, ordinary seashells, krill, pteropods, what is called coccolithopores, et cetera, will have a much harder time, and maybe impossible time, to make their seashells. Now let's look at solubility. If you put sugar in water, it's going to dissolve. Now, but if you put too much sugar, it won't. It will dissolve down to the point that the water is saturated and can hold no more sugar. Then you put the sugar in and it's not going to dissolve. But if you put aluminum, for instance, in, it's not going to dissolve. It's going to sit there forever. There'll be a few ions go into solution, but not many. And so that's what we call solubility. Calcium carbonate is an interesting substance. As we go deeper with calcium carbonate, it becomes more soluble. Pressure affects solubility in calcium carbonate. That's extremely important. You sort of think, well, great, so what? Well, the answer is if you have calcium carbonate in a seashell at the top of the ocean, you will find out it is not soluble. And there's a balance between the calcium carbonate and the bicarbonate ions and the hydrogen ions. But as you start going down, the calcium carbonate starts to get more and more soluble. This is solubility and its depth. And as you go down, it becomes more and more soluble. But it gets to here, and it says, oh, I could solute, but nope, we still have this many calcium carbonate ions running around, and it's still firmly saturated, just like the sugar. It's not going to dissolve. But as it goes deeper and deeper and deeper, at some point, it reaches a point which we call the saturation horizon. And at that point, at that depth, anything below that depth, calcium carbonate will dissolve. And it will dissolve into the ocean. And if you're a seashell, it will dissolve. The seashell will dissolve over time. And what's happening, though, as we take calcium carbonate ions out of the ocean, if we take the carbonate ions out of the ocean due to the buffering, when the hydrogen ions come in and form bicarbonate, when you do that, we have less calcium carbonate, and you will then find that the saturation depth is less. The point of all this is a seashell is starting to where it will dissolve lower and higher and higher and higher. Used to be seashells could go down to 500 meters, it'll be 400, then 300, then 200. And when the saturation depth reaches the ocean surface, as it will, seashells will be unable to grow of most types. Now, calcium comes in two basic types, calcite and aragonite. And it's just, they're the same chemically, but crystalline structure is different. And it turns out that aragonite is much more soluble than calcite. And so the aragonite saturation horizon is higher than the calcite. And so animals that are seashells that build their structure out of aragonite are going to dissolve sooner than animals that build their structure out of calcite. This is a graph from the United States National Oceanic and Atmospheric Administration that shows what they predict at our current rates of CO2 emissions, the aragonite saturation depths to be in 2020, okay, 2040, and 2090. You will see that in 2090, most of the Arctic and Antarctic, the saturation depths are 0. At that point, no seashell animal that makes its seashell out of aragonite is really going to be able to live there. But that's a huge problem with the food chain. Coccolithophores are little animals that make these little things called coccoliths. These are just the remains of them when they die, and they make them out of aragonite. And so foraminifera, et cetera, coccolithophores, krill, have calcite shells. However, corals, pteropods, and crustaceans, which include krill, have aragonite shells. And they will be unable to live as we continue to acidify the ocean. They're much more vulnerable. Now, the effect is much more pronounced on these aragonite creatures like crustaceans and pteropods. Unfortunately, these creatures make up most of the polar food web. And as we saw, as NOAA says, the aragonite saturation depth will be at the surface. It was going to have immense effects. Models show the entire Southern Ocean will be unsaturated in aragonite by 2100. And things like pteropods and krill, which make up a good 80% of the Arctic or the Antarctic food web, will not be able to grow. This is from NOAA, and they put a pteropod at 0 days, and they put it in the acidity that you're expected to see by 2100. And you can see that its shell has just dissolved. And it's especially important in juvenile pteropods and krill and other crustaceans that are trying to grow a shell. They won't be able to grow them in the first place. This krill is one of the most abundant food sources on the planet. The mass of krill exceeds that of the mass of humans. Maybe one of the most populous species in the world. They have a huge need for carbonate because krill molt, and they lose their shell every week, 3 weeks, 4 weeks. Different species have different, and depending on their growth rate. So you can't say every krill loses its shell every 7 days, but they do lose their shells within a week to a month. Well, then they have to grow a new shell. And if they can't grow the new shell, that's it for the krill. Further, krill, every day, if it's got a diel or a daily circulation where they'll come to the surface and feed and then go down 1,000 feet. And then they'll come back to the surface and they go down 1,000 feet. Well, the aragonite saturation zone, they're going to be going more and more into the aragonite saturation zone. And when they go down, they're going to start dissolving. Now, are they going to dissolve day one? No. But it's just going to make it harder and harder for juvenile krill to grow and adults to live as they start diving into the waters that are unsaturated with aragonite. This then is going to change. Another thing that's going to be hugely affected is coral. Coral uses aragonite. Coral has two whammies coming at it, two really bad things: aragonite saturation, but the other one is corals are killed by warm water. 2 degrees up can kill coral. Coral actually, in every coral, except cold water coral, there's a little symbiotic algae that lives inside the coral. And the photosynthesis provides the coral with energy. When coral gets warm, it expels its algae. It's called coral bleaching. That's why the coral looks white. And in one huge event in 1998, when the temperature got so high, we lost about 30% of the world's coral reefs. There are many scientists that now believe that we will lose almost all of our coral reefs just within a couple decades. On land, carbon dioxide is removed by photosynthesis. In the ocean, it's from calcium carbonate formation. CO2 comes in, it forms carbonic acid, bicarbonate, carbonate, and it's the carbonate. But as we lose carbonate, then we're going to lose the ability to take CO2 out of the ocean water. Basically, there's a finite amount of buffer, finite amount of CO2 absorption in the ocean, and when we use it up, it's gone. Now, this is a huge pump. It's things like whales, seals, I don't care what it is, even little phytoplankton die and they sink to the bottom. That's where that huge amount of stored carbon that we saw in one of the first slides is. Basically, this so-called biological pump takes out about 5 million tons of carbon dioxide per day from our atmosphere. As we lose carbonate and we lose the ability to do that, it's obviously going to have very bad effects on our ocean. And these graphs here show something else. There's a whole subject which I could give a talk on called geoengineering. What can we do to the planet that will help buffer or help reverse this CO2? And one of the things that's been suggested is if you look in the oceans, there are some very, very productive zones, the Arctic and the Antarctic. And you think, why in the world is the Arctic and the Antarctic so productive? Why wouldn't it be where there's warmer things? Well, the answer is where it's warmer around the equator, the ocean is very unsaturated in nutrients. There's a lot of nutrients. There's iron, nitrate, phosphate. Oh, look at the nitrates. Look at the nitrate here. Okay, look here at phosphates. Look where they are. And this is caused by the deep ocean waters, which has been down in those sediments upwelling and bringing this huge amount of nutrients to the surface. One of the things that's been suggested in ocean geoengineering is to go out into these areas. You know, this one, you can look at where the wind is carrying things away, et cetera, out into here. But you go out into these areas which are relatively unsaturated, and you dump nitrate and you dump phosphate in order to have phytoplankton grow and to seed this biological pump to take the CO2 down. We're taking 5 billion tons a day of carbon dioxide to the bottom of the ocean, but we're losing that capability because of the decrease in carbonate ions, and we have got to worry about that. And you think, well, when carbon dioxide comes in, it's putting carbonate in. It is, but remember our formula, it's putting 2 hydrogen ions in. So the 1 hydrogen ion will take its bicarbonate and put it down. The other one takes one out of the ocean. So we're decreasing carbonate. So one of the things that we can do is to do this. Now, ocean geoengineering, any geoengineering brings huge problems in that we don't know what the other effects are going to be. It's a huge area of study. There's a lot of disagreement on whether we should even attempt it or whether it will work or whether it will work great. That's the subject of a whole different lecture. This shows you just an example, though. This is off the southern coast of England, the coccolithophore bloom. a coccolithophore bloom, one, can easily take 1 million tons of carbon dioxide from the atmosphere. And so if these little things lose their ability to grow because their shells are not able to grow, it's going to have a huge effect on the ocean. And you remember this, and you remember this huge number down here of what we're taking down out of the ocean. We've got to continue that. We've got to worry about our oceans. And I, in my own mind, think that the oceans may be collapse sooner than we see the really, really radical effects of climate change on land. Another thing that will happen, though, is as the oceans warm, you will get further stratification. And you look at the different layers of the ocean, and if this layer gets very warm, it will not sink. And in fact, there are some people that say we could cut off ocean circulation. And so ocean warming and acidification are going to have major impacts on the food web, the food chains in the polar regions. It's not a hypothetical problem. If you look and go Google or Bing or whatever your favorite search engine is, Washington, Oregon oysters. And you will find out that in the states of Washington and Oregon in the United States, their oyster fishing industry has collapsed because of ocean acidification. And they can no longer, the little larva oysters will not live. And this is a huge hundreds of $1 million problem for these areas because they have collapsed because the oysters can no longer grow shells due to acidifications. So let's take an individual look now at some of the Antarctic creatures, and then we'll go to the Arctic. Penguins, of course, are sort of the signature of the Antarctic, and the penguins are lucky. They have no natural predators on land. There's a few birds called skuas that fly around that like baby penguins. But you can walk right up to the penguins. If you get too close, they'll peck at you as they will anything that gets too close to their nest. But when you go ashore in Antarctica, you'll see, like 400,000 Gento penguins or 500,000 of this or that. These are actually king penguins on South Georgia Island here. And you've got chin straps, this one jumping out of the water and so forth and so forth. But anyway, let's look at penguins. Just as a general rule, the smaller penguins inhabit warmer areas up near the equator, like the Galapagos penguin, and the larger penguins are closer to the pole, like the emperor penguins. Moving for penguins, you think sea levels rising, it's really not a realistic object, a realistic alternative, because the total area available for all penguin nesting is sort of the size of New York City. If you look at Antarctica, a lot of times it'll be ocean, mountain, and there's just no area available. And so moving's not really a good option for penguins. Sea level rise, therefore, is going to have a major impact on penguins because most of the areas where they do nest have a very small slope. Adelie penguins have had a catastrophe. Adelie penguins like to use ice to rest on, and they'll go out in the ocean and they'll come up on the ice, and that's where they feed from. They're not open ocean penguins. They're not pelagic, if you will, to go out in the open ocean and stay for days and days and days. With the loss of ice, you can see what is happening to the penguins. This is Paulette Island. There's the graph for Adelie penguins on Anvers Island. They breed earlier than other penguins. With the increased moisture, that means more snowfall. And therefore, they like to breed on rocky ground. It's really funny to stand under and watch, and you'll see a little penguin waddle up with a little rock. He'll put it in his nest, and he'll go away, and the next penguin will come over and grab the rock and put it in their nest. They're constantly robbing each other's nest, trying to build nest. But you can't lay the eggs in the snow. If you do, they become rather addled, and they're gone. So as they nest earlier, increased snowfall would be a problem for them. The big one, though, for all the penguins, even the ones that like open water, is that their major food supply are krill and pteropods. And in some regions, they have declined up to 80% since the 1970s across the board. And that's a huge problem for penguins, and that's why many of the species are declining. The krill also like to come up during the day and feed on algae that grows on the bottom of the ice. Well, no ice, no algae. Now, maybe other algae can take its place, but so far that has not happened. And this is problems with food chains are particularly acute where people, or not people, but animals depend on certain foods. You look at the top, that's a coyote. In the United States, we've had coyotes everywhere, and that means everywhere. There's probably never a place we haven't had a coyote. They're in the middle of the winter in Maine. They're in New York City and Central Park. They're in the desert in Arizona. They'll eat anything. And so if one thing dies out, it's not a problem. But you look, this is Joan, my wife, and a koala bear in Australia. Koala bears eat one thing, and if that one thing dies, so do the koala bears. And so the disruption of a food web is much more critical where things depend upon one thing, and we're seeing that in Antarctica. Now let's look at gento penguins. If you look at gentos, they like open water, and they've actually been increasing on the Antarctic Peninsula. However, ocean acidification and warming are going to be putting pressure on their food supply, and it's going to be interesting to see how long that increase can last. Rockhopper penguins come in three groups, and it's highly contested whether in fact there are three groups, but I'm not an expert on that, but I can tell you what I do know. But the northern rockhopper numbers have decreased about 90% since the 1970s. The southern rockhoppers are about 1 million individuals. They live a lot around the Falkland Islands and the southern coast of Chile and Argentina. They too are getting huge pressure on their food web. Emperor penguins are going to be particularly hard hit with the decrease of ice. The emperor penguins need flat sea ice for weeks while they molt, and also to raise chicks. And if that's not there, they're really going to be in trouble. And so it's going to be a real problem. And you know, if the ice breaks up and the chicks go in the water, when the chicks are born, as you can see this little gray thing, they're little fur balls. They do not have penguin feathers, and they can't go in the water. And they've got to wait till they grow. And likewise, when the big penguins molt, they're pretty much hanging out there. They're committed to the ice, and if the ice melts, they're going. Macaroni penguins are now listed as vulnerable. They've seen huge declines. The basic reason for this decline is not as much the open ice, but is the acidification and the decrease in food supply, which will only get worse with time. Chinstrap penguins, named because they have a little chin strap underneath. They're like gentos. They like the open water, but they're also going to suffer food shortages. Galapagos penguins, you know, in 1997-98, it plummeted by 77%, and then in 65%, mainly the El Nino and the loss of food supply. So anyway, the Arctic and Antarctic animals are faced with huge disruptions in the food web, which will cascade throughout the food chain. Now things like albatrosses and petrels, they're really not as affected yet, because if there's no food here, they'll fly over there. They fly thousands of miles. They go all over the ocean. You can be out in the middle of the ocean, hundreds of miles from land, and there they come. They follow ships and roost at night. Seals are also affected because they eat a lot of krill, and they eat a lot of fish that eat krill. In 1 year, a single fur seal in the Antarctic can eat about 1 ton of krill. No krill, no fur seals. So let's look at the Arctic. This, as I said earlier, is Svalbard. Some people call it Spitsbergen. It's very 500-600 miles north of Norway, really up in the Arctic, about 80 degrees north latitude. As we said earlier, the Arctic and the Antarctic are different. Antarctic is water surrounded by land. Arctic is land surrounded by water, and that has major effects. But both of them have one problem. In the Antarctic, it's pretty well insulated, but the animals can't move southward to compensate for climate change because of the mountains. In the Arctic, the animals can't move northward because of the ocean, so they're pretty well fixed where they are. It's interesting, even the animals living on mountains, if you live on a mountain in climate change, you can go up. You know, if we're going to get warmer now, as it gets a little bit warmer, you can move up. And even warmer, you can move up, but when you get to the top, you can't go up anymore. So animals can migrate up through the zones till they get to the top. Polar bears are really interesting animals. They frequent trash dumps a lot where I used to be. But anyway, they fixed that by now. Their white and yellow fur shields them. They have claws that are almost cat-like to grasp seals, you know, with the seals making a real dive for the ocean. And the feet actually have fur on them, unlike an ordinary bear that would not. They have small ears to avoid the loss of heat, and their skull is elongated, so as the air goes in, it gets warmed more. And they can really enter the fasting hibernating state anytime they want to. and are up a lot during the winter if they wish, and they only have 4 mammillary glands, unlike 6, because of a smaller litter size and just trying to keep energy down. Their favorite seal is a ring seal. They'll polar bear eat just about anything. I mean, they think they've died and gone to heaven if they find a whale carcass on the beach, which is blubber, because they only have a few weeks that they have to put on enough fat, basically to last for a year and raise a pup. But on the Hudson Bay, where a lot of polars are around Churchill, the ice is already breaking up 3 weeks earlier and depriving them of their feeding, because they go out on the ice and try to catch seals when they come up. Ring seals rely on ice for breeding, feeding, and pup rearing. They'll actually build dens out on the ice. Well, if that den, because of rain or warmth, collapses, that pup isn't really able to survive, plus that they'll get found by a polar bear. Harp seals are further south, and they actually are moving up north, and they can do that. The bad news for harp seals is as they move north, they're going to start getting more and more acquainted with polar bears, and that obviously would be bad. The decline of ice on the Arctic has had a huge effect on the food web, and let me show you one of the reasons why. If you look at the Bering Strait, you look over here, clear over into the Fram Strait, clear across the Arctic Ocean, you have ice. But where are the main areas of food production? They're near the shore in the shallower waters. And so as the ice melts, really it's sort of a who cares if this ice out in here at the North Pole is still frozen. Polar bears can't get out there, and hardly anything else can get out there. And so really where you're melting ice is in the prime areas. So maybe you've lost 60% of the ice, but in many areas you've lost 100% of the ice in the prime feeding areas. And again, the Arctic, the species can't move north, but other species are coming up from the south. And brown bears and grizzly bears are now moving up into polar bear range, into the southern range of polar bears. Red foxes, which are particularly good at hunting Arctic foxes, are moving up into the Arctic foxes. And the forests are replacing the tundra, and Arctic foxes just don't live well in the forest. We talked earlier, large pines are coming in, and that further exacerbates climate change. A real problem, and this one probably won't occur for 500 to 1,000 years, but is ocean circulation. What happens is when the Gulf Stream comes up, it's really cold and it sinks, and then it comes back down. See the down. And when that comes down, what if this stops sinking? What if it gets warm enough and the Gulf Stream circulation is cut off? We don't think that will happen, but if it does, it's going to be an absolute disaster. Anyway, that is the story on what climate change is doing to the Arctic flora and fauna, and be happy to answer any questions. Thank you.